In this short video, we'll see why the Petersen graph is not Hamiltonian. So we've encountered the Petersen graph a number of times before. One time we used the Petersen graph as an example to find the girth and circumference of a graph. Remember that we found by brute force that the girth of the Petersen graph was 5, right? The Petersen graph doesn't have any 3 cycles, nor does it have any 4 cycles in it. And we also said at the time that the circumference of the Petersen graph was 9. And I think in class I just said something like, I don't know, just look at all the vertices and just kind of convince yourself that there's no way to do it. But we didn't actually see a good proof for why the Petersen graph didn't have a cycle of order 9. So since the Petersen graph has 10 vertices in it, a cycle of order 9, a 10 cycle, would be a Hamiltonian cycle. And so what we're really saying by saying the circumference of the Petersen graph is 9 is that there's no Hamiltonian cycle. So why isn't the Petersen graph Hamiltonian is the question. Well, let's prove it. So notice I haven't labeled these vertices at all, and that's because I want to, so we'll just give ourselves a Hamiltonian cycle in the Petersen graph. So we'll start by saying suppose P is Hamiltonian, and then let C be V1, V2, up through V10 and back to V1. So let our cycle be this. So this is why I didn't label the original Petersen graph here, because I don't want any confusion here. I'm not saying any of these vertices are any particular vertex over there. I'm just giving myself a Hamiltonian cycle of the Petersen graph. And then I'm going to show that we arrive at some sort of contradiction. So remember that P is cubic, right? i.e. 3 regular. And that the girth of the Petersen graph is 5, right? No 3 cycles, no 4 cycles. And so we'll actually use these two properties to conclude that the Petersen graph cannot be Hamiltonian. It follows from these two properties of the Petersen graph that it's not Hamiltonian. All right, so how does this work? Here's my Hamiltonian cycle, and then since it's cubic, since P is cubic, V1 has to be adjacent to some other vertex on this cycle. Now it can't be adjacent, it's already adjacent to V2 and V10. It can't be adjacent to V3, nor can it be adjacent to V4. Otherwise, we would have a 3 cycle or a 4 cycle. By symmetry, it also can't be adjacent to V9 or V8. And so V1 must be adjacent to V5, V6, or V7. Now, by symmetry, right, V5 is 1, 2, 3, 4 away from V1 in the cycle. V7 is also 4 away from V1 in the cycle, right? 1, 2, 3, 4. So V5 and V7 are essentially the same. We could swap V1 and V10. I guess we could swap the order of the cycle. So we don't need to consider those two cases separately. Those are the same. So I'll say without loss of generality, we have two cases, V1, V5 is an edge, or V1, V6 is an edge. So we'll deal with this V1, V5 case first. All right, so here's my cycle again, and this is going to be case 1. We'll assume that V1 and V5 are adjacent. All right, well, V10 is also just degree 2 in the cycle, and so V10 is adjacent to some vertex also on the cycle. It can't be adjacent to V9, V8, or it's already adjacent to V9, sorry. Can't be adjacent to V8, that would produce a 3 cycle, or V7, that would produce a 4 cycle. It also can't be adjacent to V2 or V3, so it must be adjacent to V4, V5, or V6. In either of those cases, though, or in any of those cases, if I make it adjacent to V4, I now have a 4 cycle, V1 to V5 to V4 to V10 to back to V1. I would have a 4 cycle, so that's impossible. We can't have V4. If I make it adjacent to V5, then I have a 3 cycle, V1 to V5 to V10 back to V1. So it can't be V5. And then let's see, V6, I also have a 4 cycle, V1 to V5 to V6 to V10 back to V1. I would have a 4 cycle, and so that can't happen either, and so this is impossible. I would have a 3 or a 4 cycle in any case. And so let's move on to case 2. So it must be the case then that V1, V6 is an edge. So it must be the case then that V1, V6 is an edge. And again, V10 has to be adjacent to, can't be adjacent to V2 or V3. It has to be adjacent to V4, V5, or V6. Can't be adjacent to V6. Can't be adjacent to V5. Those would produce a 3 cycle and 4 cycle respectively. And so V4, V10 must be an edge. Now that doesn't produce a 4 cycle nor a 3 cycle. However, now look at V10. So V10, 1, 2, 3, 4. I now have a vertex on the Hamiltonian cycle that's adjacent to one distance 4 away on the cycle, V10 to V4. But that's exactly the case we had up here if we sort of generalize. I had V1 adjacent to 1, 2, 3, 4 to a vertex 4 away from it on the cycle, and we saw a contradiction. And so now, so we know that V4, V10 is an edge. This is now case 1 with V4, V10 replaced with V1, V5. It's exactly the same situation, and then we would run into a contradiction. And so this proves that the Petersen graph is not Hamiltonian. All right, that's it for this video. In the next video, we'll see a connection between the connectivity of a graph and Hamiltonicity. I'll see you there.